Well, I'm pleased to be able to welcome everybody to this webinar hosted by the Bowman Center for Sustainable Energy. The Bowman Center is a national sustainable energy think tank. We are all volunteers who have lived and worked across Canada. And in the spirit of respect and friendship, we acknowledge that our office, which is located in Sarnia, Ontario, is on the traditional territories of the Three Fires Confederacy. Today, I'm delighted to be able to welcome everybody to a presentation delivered by Dr. Sahil Asgarpour. He is the President, CEO of the Petroleum Technology Alliance Canada, also known as PTAC. Bowman Center has been able to participate in PTAC and the various member companies PTAC, as we have been focused on hydrocarbons as just one aspect of Canada's sustainable energy future. Today, Dr. Asgarpour has a topic pertaining to the building a robust clean tech industry while promoting the sustainable oil and gas business. And whereas he's normally based in Calgary, Vancouver, and this presentation is being recorded so that we will be able to share it at some point in the future. Sahil, thank you very much for joining us. I relinquish control of this webinar to you.
Well, Marshall, thank you for inviting me. Really appreciate that. And it's my pleasure to talk to you. I thought maybe we can have dialogue. So any place that you want to have a questions or you have a comment, etc., please go ahead and pose your question or your state your comment. And I think, as you can see, the title is Building a Robust Clean Tech Industry. And I was looking at actually the world economic growth and what is expected by 2030. And it seems that the world economy is gonna grow by 40%. And so then we realize that oil and gas has always played a major role in providing reliable source of energy. The question is the way that we are producing and we are consuming oil and gas. If we want to get to net zero, we have to change it. We have to use different approach. So this presentation is about how clean tech can help us achieve net zero, or at least try to reduce emissions significantly, talk about the challenges and also opportunities, etc., in doing so. So let me start with this agenda, which is essentially, let's talk about greenhouse gas emissions from oil and gas sector. And by sector, of course, I mean, including oil sands and other sources of hydrocarbon. And then talk about the path to net zero oil and gas production and consumption. The technologies that there are key is methane emissions reduction technologies. Actually, they can economically reduce greenhouse gas emissions. CO2 emissions reduction, this would be mainly through CCUS or CCS, estimator ratio optimization, eco-efficient technologies. Again, these would be something for reducing greenhouse gas emissions from production of oil and gas and hydrogen. Of course, some of these technologies are extremely costly. Some of them, they have major challenges. But if we want to reduce the greenhouse gas emissions, these are some of the technologies that they would be capable of doing it. Then we want to talk about PTAC's initiative to reduce methane emissions, have a discussion on CCUS projects to reduce greenhouse gas emissions, and then talk about greenhouse gas emissions from consumption of oil and gas. And the technologies, again, would be CCUS or CCS, hydrogen, nuclear technologies, and other technologies. So this shows the countries that they have made commitment to net zero. And as you can see, 70% of them, they made the commitment. The gray area is countries that they haven't made any commitment yet. You can see some countries, very few of them, that they have already achieved net zero. Some are gonna meet the target by 2030, but by far the majority are either 2050 or beyond 2050 that they are targeting to reach the net zero target. Here shows essentially greenhouse gas emissions from various countries. As you can see, 5 countries, China, the United States, India, Russia, and Indonesia, they represent 50% of greenhouse gas emissions. Canada greenhouse gas emissions, as you can see, is around 1.6%. So where is this greenhouse gas emissions is coming? This is a source of greenhouse gas emissions. When we look very carefully, we can see actually, like transportation, majority of it is from consuming products from oil mainly and gas. The burning for generating electricity and heat, and some of the other areas are all related to hydrocarbon and fossil fuel, essentially. When it comes to oil production from Canada and also the consumption, you can see that we are producing around 4.8 million barrels per day. 2.27 of it is internally consumed. In addition, we import 0.55 million barrels, and we consume 3.5 million barrels in Canada. 38% of Canada's energy demand is from oil, and with respect to gas, is 36% of, again, energy provided is coming from natural gas. Again, we are importing some gas, but exporting significantly more, and our production is 16 BCF per day. So this shows essentially where the greenhouse gas emissions are coming by sectors. When you look at it, oil and gas production, part of the electricity or majority of electricity generated that has greenhouse gas emissions, and then transport and some of the other areas that are all related to oil and gas. I would say around maybe 70 to 75% of it is coming from oil and gas. So again, with respect to oil and gas production, for conventional oil, methane detection and mitigation technology is extremely important. Also, eco-efficiency technologies. For oil sands is reducing steam-oil ratio, eco-efficiency technologies, but also technologies that can reduce oil sands production of CO2 would be CCUS or potentially nuclear. On the consumption side, CCUS or /CCS, hydrogen and others, and electrifications would be key technologies. So this shows essentially where the majority of greenhouse gas emissions is coming from. Production of oil and gas, essentially we can see 78 megaton is coming from upstream conventional oil and gas. Methane emissions is around approximately 55 megaton. And that number actually is debatable because the way it has been historically measured was not correct. It was done through some coefficient, etc. And now that we are measuring it in the field, we are seeing actually the numbers to be much higher. So I would like to maybe talk about the initiatives that we have taken to reduce methane emissions. This shows the kind of the ecosystem, innovation ecosystem that we have created and various initiatives. It starts with a network, and the function of network is to connect people, ideas, projects, technologies, etc. The network was a collaboration between PTAC and CREAN, and also what we have done, developed a technology roadmap for pursuing some of these activities. Then the next level would be applied research projects done through Alberta Upstream Petroleum Research Fund. Through this program, we have launched and completed around 500 projects on 5 environmental areas. One of them is air quality, and subset of air quality is methane, which you are going to see some of the projects that they were launched. And the byproduct of these would be 2 things. One would be essentially helping policymakers and regulatory bodies to come up and develop smart policies and regulations from this peer-reviewed applied research, but also is development of best management practices that has reduced cost and environmental footprints significantly. The small and medium-sized enterprise, it's the work that we are doing to help SMEs commercialize their technologies. So essentially, this is market fit analysis, getting them in touch with producers, promoting their technologies, and helping them develop, field test, deploy their technologies. So the next level is the technology development. You can see that 9 technologies for reducing methane emissions have been developed. And these technologies essentially was done through formation of consortia. And again, with a consortium, what we do, we would secure funds, we secure sites, we help technology companies develop their technologies. Next level would be the lab and field testing facilities that we put together. So you can see later on, there were 16 universities and research centers, plus 14 producers. They dedicated over $1 billion field testing facilities to do so. This work is in collaboration with Alberta Innovates and NRCan. NGIF is part of it, and we have been able to actually field test enough technologies that would have capacity to reduce oil and gas sector's methane emissions by 48%. The next level is the deployment of those technologies. Through 2 programs, we have provided up to 75% cost of installation and equipment, and this way give first-hand experience to producers to, once they kind of get a good feel about these technologies, then they would go and buy them at a scale, those equipment, etc. On the global outreach and trade missions, etc., what we have been doing is trying to help SMEs export their technologies globally and increase market uptake of their technologies. On the disseminations of results, again, we have events, workshops, technology information sessions, which would help us disseminate the results. So the bottom line in terms of our grand vision is that we set the target of, as a goal, reducing or developing enough technologies to reduce methane emissions by 45% by 2020 at a cost of less than $5 per ton of carbon dioxide. We actually met this target and exceeded last year, where last year we announced that our technologies developed through PTAC consortia with, of course, massive collaboration with many, many organizations. Now they have capacity of reducing methane emissions by 48%. Our long-term vision is to increase technology capacity to 90% by 2030. And of course, part of it is also about methane detection technologies. So this is a list of best management practices that we have developed through the applied research program that I just mentioned. This would be some of the studies that actually were conducted related to methane. These are applied research, again, studies. All of them were done by universities and reputable engineering firms, and are peer-reviewed studies. This is a list of some of the methane detection technologies that they were demonstrated. And we are using sophisticated sensors, plus using either drones or trucks or aerial or handheld, stationary, etc. One project that we did, which is a relatively big project, an area of over 2,500 square kilometers, operated by 30 producers, and there were 200 large facilities. We went and measured methane emissions equipment by equipment, and we repeated regularly. And that was essentially to come up and find the optimum frequency for doing this type of tests to be able to detect methane emissions. We did another study, again, same area, not same area, but similar size, 2,500 square kilometer. This was done in in central Alberta. The other one was done in Rocky Mountain House. But the other site, what we did, we used various technologies like drones versus aeroplanes versus trucks and stationary sensors, and then started looking at combining these technologies to see to find the best way of detecting sources of emissions. The work that we have done to develop, commercialize, and deploy technologies, this is an example of it. This was done in 2009 when nobody really paid attention to methane. Methane was not on anybody's radar screen. We started our work in 2008 with this technology that captures light hydrocarbon from compressors and then utilize it in the field as fuel. And then so the impact of this technology is right now is like taking 170,000 cars off the road, but saving industry $20 million in reducing cost of fuel. So far, 8 megaton of CO2 equivalent have been reduced. So to put things in perspective, this would be equal to over $1 billion CCUS project in terms of how much emissions have been reduced from this technology. I talked about this testing facilities. These are the organizations that they provided support and dedicated their facilities for doing this work. The facilities covers from east to west, north to south, coast to coast to coast, and as you can see, everywhere. And the beauty of this was that at no cost to technology providers, now we are able to field tested technologies, also lab tested technologies, and help them to overcome the biggest challenge that they were facing, and that was the valley of death challenge, because they had problem in secure funding and secure sites for commercializing their technologies. List of 9 of these technologies that they were developed through PTAC, and they have capacity of reducing the oil and gas sector's methane emissions by 37% is shown here. By the way, when I'm talking about the sector's methane emissions, doesn't mean just in Canada. Many of these technologies are globally being used, especially in the US. This is a list of 23 technologies that they were field tested through this either consortia or the field testing facilities that I just mentioned. Again, collectively, they can reduce sector's methane emissions by 39%. This is a list of 16 technologies that we have actually done deployment and demonstration, and they have capacity of reducing sector's methane emissions by 48%. So what are the gaps? I think the gaps for methane is oil and condensate tanks. We still are challenge finding a technology. This is something that we are working. We have launched numerous projects to address this. The other one is surface casing vent flows. These are wells that leaking methane, and to put things in perspective, an average well, its emissions is equal to an average cow. Engine methane sleep is another technology areas that we are working on, and this is unburnt methane coming from not complete combustion. We have looked at the inventory of all of the equipments that we have. As you can see, the ultimate counts in that column shows how many of these equipments are out there. On the first one column, we show that reduction per year per unit of these equipment. And then the 2030 reduction essentially shows what is the expected if we just deploy all of these units, how much we would be able to reduce methane emissions is 26 megaton. So these technologies have actually reduced methane emissions significantly. This is coming, this kind of a slide coming from the Alberta Energy Regulator. It shows how much methane emissions have been already reduced, and majority of this reduction are due to these technologies, but also with the help of regulatory bodies that they set the target, etc. And I can tell you that majority of these technologies are actually making money for producers. Not only they are reducing their methane emissions, but they are making money by deploying these technologies. So any questions on methane before I go to carbon capture, utilization, and storage? Okay, if not, then the next one is CCUS, which essentially can help us to, achieve cleaner oil and gas. It would help decarbonizing heavy industries, cement industry, etc. Low carbon power, low carbon hydrogen production, and of course CO2 based industries. The world requires numerous of these technologies to be developed, and this is actually coming from the source is International Energy Agency, that shows that from now till 2030, we have to increase the number of CCUS drastically. As you can see, it's something that potentially it's going to be a major challenge to get all of them happening to meet the milestones of 2030 to get to the net zero by 2050. The biggest challenge of CCUS is cost. The cost is really high. I mean, in Canada, we are talking about around a carbon price of $175 per ton of CO2 to make it economic. Pathways just announced that they are going to spend $22 billion by 2030 to get to a target of reducing methane emissions by around 22 megatons of CO2 equivalent. So, and that is essentially the target would be the CO2 that comes from generating steam for oil sands, then chunk of it then would be sequestered, etc. Canada has experience in this area. There are still some people question whether sequestration is gonna work and is not gonna leak later on, etc. But the experience and the work that has been done so far shows that actually this could be, there is no sign of this happening so far. So the next one is about hydrogen and the challenges of hydrogen. So this is kind of a schematic of, how hydrogen can be utilized, the hydrogen economy. Again, the challenge with hydrogen is, for generating hydrogen, I mean, it's either green or blue. Green hydrogen, the costs are extremely high, could be 2 to 3 times higher than even blue. And the challenge is that, there are numerous technical challenges. First is with respect to transportation, that if it's carbon steel, then it cannot really be a good carrier for it. Its safety is one of the considerations, especially if you are going to have a station everywhere to provide fuel for cars, etc. In my opinion, the area that really hydrogen could be really effective would be used as a storage. And also the other area that can be used would be for transportation, like for aeroplanes, or also for big heavy trucks, etc. So again, this is another schematic of where hydrogen could be generated, as I said, from electrolysis, etc., or through methane reforming, and then be utilized various places. Again, this would be applications of hydrogen in this slide. And as I mentioned, safety would be a challenge, a massive infrastructure. This would require huge amount of money. Stations are not in proximity to the pipelines, etc. So you can just see some of the challenges that we have. So I have to move faster because it seems I'm running out of time. Nuclear technology, again, here shows the cost, being reliable, emission-free, etc., as opportunities or pro. And then the cons would, of course, would be high capital cost and technical feasibility and economic viability, etc. We did 4 phases of studies to evaluate application of nuclear for oil sands. And the bottom line is the study results says that we cannot use water-cooled reactor. It wouldn't generate enough temperature. High temperature gas reactors were feasible technically. And then we actually evaluate few of those reactors, as you can see. the biggest challenge right now is not even economic, because when we did the economic evaluation, if we use very large reactors, like around 3,000 or 4,000 megawatt reactors, then the big challenge of it is it takes a long time to go through the process of getting the license and then deploying it. As you can see, we are talking about timing would be around post 2040. So in summary, I think achieving net zero requires robust innovation, policies, regulations, social, and more important than any of them, behavior dimensions. I think we gotta really change the way that we are using energy. Transformation of the end user sector and energy supply chain would be another important area. Integrated planning. We cannot just look at these things just in isolation in oil and gas. We have to look at work with renewables, work with nuclear, work with everybody. Otherwise, it's not gonna happen. Understanding the future trajectory of technologies, what is happening to solar energy, etc., that the cost is going down drastically. And I think we should really focus on low-hanging fruit. Methane emissions is a good example. We talked about reducing methane emissions, again, with focusing on low carbon electricity, CCUS, hydrogen, and batteries, looking at low hanging fruit in those areas. Working on SMR, especially for areas that are very remote, would be an idea. And then again, the path to net zero and launch of numerous mega projects. The question is, are we ready? Are we developing enough human resources, highly qualified professionals, skilled laborers, etc.? Because that by itself is a mega activities. And research and development, of course, would be very important to reduce costs and overcome some of the technical challenges. So I ran out of time. So I'm sorry for that, but I would be more than happy to answer your questions. I think you are muted.
There we go. Okay, I think we're fine now. But again, thank you so very much for joining us, Sohail. There's a couple of questions. There was one that was in the chat function already. Tim Belsky is asking about the methane mitigation and Bitcoin mining. Is there any exploration? Is that something that PTAC has been looking at with regard to particularly the Alberta economy? Is using methane, capturing it and using it to power basically the Bitcoin mining, generating electricity. Is that a consideration, or is that even on the radar screen for the topics that you've been chatting about within PTAC?
I mean, to be honest with you, I'm really way against this Bitcoin mining. I mean, the amount of greenhouse gas emissions is equal to what Norway is generating right now, the whole country. And the question is, for what? Why and what is the objective? The technologies are there to reduce methane emissions no matter what the application is, because what they are using is using cheap natural gas to generate electricity to run those big computers. So the technology is there. But the whole exercise of it, I think that's something that really I question.
Okay. To move to a different topic pertaining to hydrogen, as in one of your slides you mentioned that your diagram shows taking hydrogen to produce ammonia, particularly for agricultural uses and for export. Have you Are you aware of other research pertaining to liquid organic hydrogen carriers, LOHCs?
Yes, I'm actually aware of. We talked about it. I attended just this past weekend Energy Council, and there were two presentations made by David Lazal and also by Amit from University of Alberta, using that type of technologies, and then using hydrogen as a carrier. Those like what you just mentioned as a carrier to just move hydrogen, because that would overcome some of the challenges of transporting hydrogen.
That's correct. We've sponsored some research already pertaining to liquid organic hydrogen carriers. We think that there are a couple of molecules that are particularly interesting.
Yes.
Methanol, of course, is one, and dibenzyl toluene is the other. Both
That's
of them
right.
are commercially available right now, but have tremendous promise to be able to move hydrogen from point of generation to elsewhere.
Right.
Um,
Yes.
And this question from Peter: in your view, how much oil and gas will we still be burning in 2050? And how will we offset those emissions to actually reach net zero? There's two questions there. How much oil and gas will we still be consuming, generating, producing, and burning, combusting by 2050? Any thoughts, any forecasts?
Well, no, I don't have a forecast, but of course, it would be great if we stop burning natural gas, because, and if we are burning it, then we have to use CCUS to offset that. But I can tell you right now what Pathways is working on. By 2030, I think they are talking about, as I mentioned, significant reduction from their greenhouse gas emissions. Their target, they say they are committed to 2050 target. That's what Pathways have announced, that they are going to essentially sequester or get rid of all of the CO2 that's generated from burning natural gas.
Okay, so in terms of emission control, there's predominantly a focus on CCUS. Is there anything else that PTAC has been looking at for offsets to be able to either for the industry as a whole or for individuals, parts of the petroleum industry, to be able to say that they have an offset that can achieve net zero?
Well, the biggest area of emissions is actually not coming from production of oil and gas, it's coming from consumption of oil and gas. And the solutions to it seems to be, at least something that many people agree, would be converting this hydrocarbon convert it to clean electricity or hydrogen to some extent. The clean electricity makes really good sense. Hydrogen also for storage would make sense, in my opinion. The challenge of doing this is that the cost of doing that, because I did a very rough calculation to see what happens to our grid system and in terms of increasing capacity, etc. It seems that we have to increase the capacity of grid system by 250%. So that means the money that we are going to be spending, it would not be in, say, billions of dollars or tens of billions. It would be in hundreds of billions of dollars. And what the problem that we have had before in Alberta, we did 3 projects. Each of them cost around $7 billion when we were doing the oil sands expansion. And these projects were considered at that time as mega projects. And these the $7 billion projects resulted in major cost overrun, shortage of manpower, skilled labor, highly qualified professionals, and actually loss of productivity, etc. Well, these projects that we are talking about, they are not $7 billion or $20 billion. They are not even $70 billion. They would be more than $700 billion. So how are we gonna manage it? It's just a practical aspect of it, which is very, very important. And that means we gotta, if we really are serious, we gotta start finding solutions now, start developing the skill labors that we require and highly qualified professionals, and especially developing people that they can manage these mega projects. Because when we were running these $7 billion projects, that required completely different skill than the guys that they were running $50 million projects. And then now we are talking about 2 orders of magnitude higher for do that. And then so that requires completely different skills, and do we have it? So those are the big challenges.
And they are big challenges because you know, and I know, and we're trying to promote that the energy sector overall in Canada represents somewhere between 6 and 10% of our GDP. We need to make sure that we plan, prepare, and deliver a robust transition plan to make sure
Exactly.
that everything happens correctly. Now, there is a comment and question from Eddie Isaacs, and I know you know him very well.
Oh, yeah, right.
That regarding the work on methane, that the information you shared, the slides you shared about the methane reductions is really quite impressive. Other than presentations such as this that we help promote as well, what else are you able to achieve? How else can this be done so it's the reduction of methane emissions is better known and understood?
No, that's an excellent question. And, you know, it's the problem that we are running at PTAC. We are a neutral facilitator, and it's kind of our structure is to just focus on doing the work, heads down, and doing the work, and not really put huge amount of energy on communications. But this is something that we really need to do, and we haven't done a good job of it. I mean, in terms of the impact that methane can have, is just huge in terms of reducing greenhouse gas emissions. And the beauty of it is, of course, is cost effective. I was talking to a technology providers that recently that he was saying, this is exactly what Eddie said. He says, well, people need to know what is happening here in terms of the impact, etc., and making sure that we would move it to a different level in terms of reduction of methane emissions. As I mentioned, we don't have technologies for some of them right now, but it would be so important to work on developing those technologies. Communicating this information globally is also very important. We kind of are launching some international programs trying to promote Canadian technologies globally. The next initiative is a trade mission that we are going to have during CERA Week in Houston, and taking several of these technology providers over there to kind of showcase their technologies and then capture some of the US market opportunities.
Part of the communication issue, of course, is that more and more people are becoming very much aware of Scope 1, Scope 2, and Scope 3. Scope 1 being directly from the project, Scope 2 are the indirect ones, and Scope 3 are from the final consumption and use of the products. Again, focusing on the methane emission reductions, is there an opportunity to communicate that better through a better understanding of the Scope 3 emission reductions. And taking this on a tangent, we talked briefly um, about nuclear power. Is there the opportunity for small modular reactor to either produce hydrogen to help with emission reductions or to offset things entirely? I realize that's a complex question, but is there some opportunity for PTAC to better explain Scope 1, Scope 2, Scope 3 emission reductions and draw into that some hydrogen and SMR concerns?
Sure. Well, there is this presentation that I'm supposed to make at the World Petroleum Congress on methane. And I think that's kind of where we are trying to prepare exactly what you said for that event. On the communications also, we have published a report, but it hasn't been disseminated properly, and that is what we are trying to do through GMI Global Methane Initiatives. All of these technologies that I talked, they are on GMI's website, Global Methane Initiatives. So people can read them. And also, I put a report together if anybody is interested. The detail and all of the information that I presented, would be in that report. So if you are interested, I can send a copy to your fellows, etc., and then kind of disseminate that information this way.
Okay, we have that noted, and we will see about adding links and additional information about the global methane initiative to our website. And because, of course, the Bowman Center for Sustainable Energy, founded over a decade ago, we've been dealing with questions about Canada's sustainable energy future for all of that time. We've been doing our own research, certainly enjoyed collaborating with you. And I note others that are on the call, particularly from the University of Western Ontario. We have enjoyed and continue to enjoy some collaboration with other academics. We see ourselves as trying to be a bridge between industry and academia, as well as other sustainable energy think tanks, because day by day, we're getting closer and closer to the expected deadlines. And we know, as I'm sure you do, that the delays that Canada is noted for need to be addressed. We need to be able to focus on doing things more quickly, more succinctly, and achieving much better sustainable energy future for the country.
Sure. And I should also acknowledge the contribution of Eddie. Eddie, when he was the head of Alberta Innovates, supported these programs, supported our activities, and so without his help, we wouldn't be where we are today. So Eddie, thank you for your mentorship and everything else.
Well, we agree wholeheartedly with any recognition that we can offer to Eddie. Very much appreciated.
Yeah, thanks.
I'm not aware of any other questions within the chat function, and I know that there's still some questions about small modular reactors. Is that correct, Ed? Small modular.
Yeah.
A slide showing methane projected reduction, all of the impressive methane reduction work underway. The projected methane reduction is modest. Is there still enough reduction available to make a significant reduction in consumer Scope 2 emissions? Particularly the SMR hydrogen production, even with the carbon capture system.
Would you please repeat that, because I couldn't hear you properly?
Well, there's been substantial emission methane reduction already is there enough left to be reduced
Oh, I see.
that
Okay, right.
this will have a positive impact on consumer scope 2 emissions, particularly as methane is being used for steam methane reforming. That's it, for hydrogen production.
Oh, I see. Right. Okay, so to answer the first question, this is just Alberta. So when you look at Alberta plus BC plus Saskatchewan, and also look at the actual methane emissions that, based on all of the information that now we are getting using the various detection technologies, the total methane emissions is around 55 megaton. And this shows that actually already 34% of it is reduced. And this is happening before even the regulations take place by 2025. And the reason that this has happened is this, what I call early adoption of technologies that actually also provided incentives for early adoption by government, saying that we give you some carbon credit, etc. So how much of it is left is approximately 65% of it is left, 65% of 55 megaton. So which is significant amount of greenhouse gas emissions. And I think the way I see it, if we overcome 3 of these major challenges that I mentioned to you, then we can potentially get up to 75% or even more. But those 3 challenges are major challenges, are not simple to overcome. After that, then we get to really extremely low emissions rate, which becomes very expensive. But that would be mainly we have many small whales that are emitting extremely small amount of emissions. So that's as far as this is concerned. Now, is this going to be in terms of amount of methane that is going to be left for doing any of the projects that you mentioned? This would be able to save more methane, so we can do even more. So the production of natural gas is going to continue the same way that it has happened, 16 BCF per day. Actually, production most likely can easily get much higher. The reason we don't produce more than 16 BCF per day is because we are limited by the market access that we have, and the US is the only country right now is essentially buying majority of the gas from us, the amount that's exported. So there are 2 different things, right? One is the production of natural gas, which is kind of function of how much reserves we have, which we have significant remaining reserves of natural gas. So we can generate huge amount of hydrogen from it if we decide to go that route. The methane emissions is also make it even bigger, because rather than emitting it, now we are conserving for consumption.
Not seeing other questions at this point. I know that we could probably start to engage in some detailed discussions. There is one question. What conversion factor are you using when converting methane to CO2?
Okay, very good question, excellent question. We are actually using a very conservative number of 1 to 25. So 1 molecule of methane would be equal to 25 times more CO2. If we look at the next 10 years, that number is actually 1 to 100. So the other beauty of methane is that when we are reducing methane emissions in terms of short-term impact, is a huge impact. It becomes actually almost the same amount of global CO2 that we are generating per year, or we can reduce. I mean, if you use the methane amount would be equal to the amount of total CO2 that is produced per year if you use 4 to 1, which is 1 to 100, 4 times more than what we are using in those calculations. So the bottom line is methane would have huge impact on the climate change for next year, 10 years. Very material impact.
Okay. And all of
So
the
we are
transition-
using this very conservative number here, looking at over 200 years period.
and all of the discussions about the projects that are underway, the reductions that are underway, the urgency that we've been promoting and you have been promoting for a very long time is it's just reinforcing the potential impact on the Canadian economy. So we need to continue this discussion with you in the future on other projects. And I'm going to wrap this up now by again acknowledging Dr. Sohail Asgarpour. Truly appreciate the work that you've been doing, leading Petroleum Technology Alliance Canada and working with us at the Bowman Centre for Sustainable Energy over the last 10 years or so that we've been around. And I truly look forward to continuing the discussion in other ways in the future. I thank everybody else who has joined us. I thank everybody else who has joined us today, and wish everybody a very safe and happy holiday season. Last word to you, Dr. Asgarpour.
Well, I just want to say that I really appreciate the invitation, and I wish all of you a happy holidays, and all the best to all of you.
Okay, thank you very much, everybody. That brings our webinar to a conclusion. Thank you.
Thank you very much.